Very well, so good morning. Today we plan to close up the part on non-standard medium access control protocols, okay, and then to move on to the introduction of the 6LoWPAN protocol stack, which is the, let's say, competitor of the Zigbee one, okay. So as usual, a very quick wrap up on where we stand. So what we did till last time was basically to introduce different kinds of medium access control protocols, and we have seen that roughly speaking these protocols can be classified into three broad classes, which is based on how each one of these protocol handles collisions, okay. And we have mentioned that the first class of these protocols is that of contention-based protocols, which means that these are protocols which allow collision, okay, among nodes, and then they try to react to collision in some wise way. Then we have mentioned scheduled medium access control protocol, which most likely are based on time division multiple access paradigms, in which collision cannot happen, okay, because the transmissions or receptions are scheduled by some kind of central entity. And then we mentioned hybrid medium access control protocol, which is protocols which somehow merge both kind of paradigms, so contention-free and TDMA-based approaches. Okay. So 15.4 is part of these hybrid protocols because it has both contention-based and contention-free kind of accesses. Last time we commented on the SMAC, okay, the sensor MAC protocol, which is the, let's say, representative of contention-based access protocols, okay. And today, basically, we close the loop by seeing a protocol which is a scheduled one, meaning it's a time division multiple access based protocol, okay, which is called SPEAR-MAC. So what you are going to see today is basically one representative of this TDMA-based protocol for sensor networks, okay. Again, as I was saying last time, there is much more than these, so always remember that these are basically non-standard protocols, okay, which means that they're not in any standard, okay, but still they are used somehow in some, let's say, practical deployments, okay. Besides these, let's say, two protocols which we have seen, SMAC and SPEAR-MAC today, you can find many more in the literature, also in deployments, okay, so don't think that this is, you know, only what is out there for sensor nodes, for sensor network. That's not true, okay, that's just a couple of representative of these two words of contention-based and contention-free protocols, okay. So let's talk about this SPEAR-MAC. So as I was saying before, this is a TDMA-based protocol. TDMA stands for time division multiple access, which means that we expect the time to be divided into time slots, okay, which are, as this stuff here says, dynamically managed. So the assignment, we expect that the assignment of these time slots to nodes, okay, so the assignment of the atomic resource for transmission and reception to nodes is dynamic, okay. Was it dynamic also in 15.4? So was it kind of dynamic assignment also in 15.4, or was it kind of static one? 15.4 had its own, let's say, TDMA-based kind of part, right? With the GTS time slot, okay? The assignment of this time slot, was it dynamic or not? Yes or not? Remember? It was dynamic in a sense, in the sense that the pan coordinator could dynamically, on a beacon interval time frame, reassign this GTS to all the nodes. Okay? We did not see the dynamic part of the assignment, but still, if you remember the periodic, let's say, structure of the beacon intervals, okay, we mentioned some time back that the pan coordinator can, in principle, change the assignment of the GTS, okay, on a beacon interval basis. Okay, so it was kind of dynamic. Okay, and something similar happens here. This is kind of more refined protocol in a sense that the core concept which this protocol is built on is this concept of reception schedule, which is called RS here. Reception schedule is basically a set of slots, so a bunch of slots in the time frame, okay, which is assigned to a specific sensor node, okay, for receiving data. Okay, so this set of nodes is given to a given sensor node, and in these time slots, that sensor node can only be active for receiving data. So it cannot use those slots for transmitting, okay, but it can only use those slots for receiving data. Okay. So in 2 lines, the protocol can be summarized in these 2, bullets in this bullet list. The first one is all the nodes which belong to the network must have one of these reception slots. Sorry, one of these reception schedules. Meaning that all the nodes in the network must have a bunch of slots which is dedicated to these nodes and which these nodes can use for receiving data. Okay? Second is that all the nodes in the network can get to know the reception schedule of the neighboring nodes. Okay? Which means that, again, all the nodes in the network must know, okay, what is the reception schedule of all the nodes which are close by. Okay? And it is very simple. Have a look at this picture in this slide. So you have basically a very stupid network with 5 nodes. Okay. Each one of these 5 nodes has this reception schedule, so it has a bunch of slots which is dedicated to this guy. Okay. And as this bullet here says, all these 5 nodes tell the other nodes what is this reception schedule. So in which slots the specific node will be active for receiving data. Okay. Take the red node here. Okay, the red node, okay, will send out a message, we'll see how, in details, to all the other nodes, telling that this guy here, the red one, will be available for receiving in a specific slot, which is in this case slot K. Okay? So the assumption in this figure is that the reception schedule is composed of one single slot, basically. Okay? So if these 4 guys here, okay, get to know that this guy here will be active for receiving at slot K, if in the next future they will have something to send to this guy, the red guy, okay, they can switch on at slot K only, okay, and send data at that specific slot to that specific node. For example, in the figure, only this node here has traffic to send to the red one, which means that it will switch on at slot K, reception schedule, and will just send data to the red node. Okay. In this way, the sender will be sure that when it will send data, the receiver will be there for receiving, will be active for receiving. Okay? In a nutshell, the core idea is that the nodes are active for receiving only in the reception schedule, which means that in all the other slots, they can be actually sleeping. Okay? Clear? So that's the, let's say, very qualitative description of the protocol. Now, there are some details which must be worked out, basically, like what is the reception schedule, how the reception schedule can be distributed to neighboring nodes, okay, how the transmission can actually take place, and so on and so forth. Okay, but still, this is the most important slide to understand the SPIRNEC. Then all the other slides are details on how to implement this concept. Okay, so is the concept clear? So that's slightly different than what happens, for example, in 15.4, because in 15.4, the GTS slots are assigned generically for being active, which means that GTS slots are assigned most likely for transmitting information to the PAN coordinator, right? In this case, slots are assigned for receiving data. So which means that in that slot, in those slots, the nodes must be on only for receiving data. They cannot transmit data in their reception schedule. Okay? So what do we need? What kind of details we have to work out to make this idea, let's say, operative? The first thing we need is basically a distributed way to assign and, let's say, disseminate the reception schedule across nodes. Okay, so we need a way such that each node, in a distributed manner, can get to know what is its own reception schedule. Okay, so can get to know which slots it will be active for receiving, and then once the reception schedule is being assigned or decided somehow, we need ways such that one node can broadcast this reception schedule to neighboring nodes, such that in turn they can get to know when they can reach the guy, okay, if they have anything to be transmitting to the guy itself. Okay? So if we are able to design this couple of, let's say, algorithms or parts of the protocol, okay, what we achieve theoretically, okay, is the following. So we achieve that each sensor node can, in principle, be active only when it has data to receive, okay, the reception schedule, or only when it has traffic to send to nodes, okay, whose reception schedule is known. Okay. So basically, we are getting rid, or we are, let's say, limiting at the optimum, I would say, what we have called the idle listening. Okay, because again, a node is only active either when he has to transmit stuff or when he has to receive stuff. Okay, the probability that the node is on but nothing is done is very, very low. So this means that we are actually limiting idle listening. Okay. Then, since a node is active only in those slots of the reception schedule, which are the slots in which he or she can receive information, okay, we are also limiting what we call as overhearing. So if a node switches on in its own reception schedule, and all the other nodes know that that is the reception schedule of that specific node, okay, this means that the receiver information, what the node which switches on in its own reception schedule receives, it's information which is meant for itself. Okay, so the overhearing of other transmission is kind of null or limited here. Okay, and then we have activity also in what is called a wake-up slot, which will be clear in the next slides. Okay, but in principle, what I want you to understand is that if we are able to actually handle this distributed kind of assignment of the reception schedule, okay, we can in principle reduce idle listening and overhearing. Okay? Fine, what is the problem here? What kind of problem you see here? Before going into the details. What kind of complexity you have here? This is fine. That's very, impressive results. Limiting idle listening and overhearing. You have to pay something, right? You have to give back something, okay? And what you give back, as we will see, is basically in the, let's say, signaling procedure to assign in a distributed way the reception schedule. Okay? Again, there's no PAN coordinator here, which means that there's no one that can decide a priori when a node can send and receive or must send and receive. Okay? Which means that the assignment of this reception schedule must be distributed. Okay? So you have coordination among nodes and all those such of procedure which cost in terms of messages, resources, and so on and so forth. Okay? Clear? Okay, so let's see how it works in practice. Okay? First of all, we have mentioned that this is a time-slotted kind of protocol, so it's TDMA-based protocol. Okay, so we must expect to have some kind of framing structure, so some kind of frame defined for the protocol. Okay, just like we had for the 15.4, which had its own beacon interval, super frame, GTS, cap, and so on and so forth. Okay. The same stuff happens here, so the same framing, the same concept of frame is valid here, okay? And what you see in the slide is the framing structure of SPIRMAC, okay? So as you can see, in this frame you have actually two parts, okay? So you have a bunch of slots, given a series of slots, okay? Some of these time slots are called the signaling subframe, SSU, okay? And some other slots are called the data subframe, DSU, okay? And then in the middle, you have a slot. The position of this slot is irrelevant, I would say, it can be also the beginning. But in any case, you have a slot, which is called WS, which stands for wake up slot, okay? Whose meaning and usage will be clear in a few seconds, okay? So we have this framing structure, okay, which means that all the nodes which take part in the network must be aligned to this framing structure, okay, which is one of the first problems we have here. Why it's a problem? Because we don't have any pan coordinator, so we don't have any beacon here, which means that all the nodes in principle can operate in an uncoordinated way. Okay, there's no, let's say, central timing signal which can be sent by no one, because there's no pan coordinator. Okay? So we assume that synchronization, so this kind of alignment in time, can be achieved through some kind of protocols, okay, which are not part of this SPIRMAC. So we assume that someone else gives us a network where sensor nodes in the network, okay, are actually time synchronous, which means that they have the same idea on when a slot starts and when a slot ends. Okay? And this can be done in different ways, can be centralized, can be distributed, and so on and so forth. Okay, so synchronization is not part of SPIRMAC. Okay? What SPIRMAC does is, given that you have this framing structure, how to use this framing structure in the best way from the access point of view. Okay? So some more parameter. You have the signaling subframe is composed of a given number of slots, which we call N here, big N here. And data subframe is basically composed of M slots, big M slots. As you can guess from this framing structure, the signaling subframe, so these first N slots, okay, are those slots which are used for building up the reception schedule assignment. Okay, so this is basically the part of the bandwidth, I would say, which is dedicated for signaling. Okay, so for building up the reception schedule assignment. Okay, so basically you cannot use this slot for delivering data. Okay, the data subframe, on the other way around, is the part of the time frame which is dedicated for sending data. Okay, clear? Okay, so let's see how the assignment is managed. Okay, so let's start from the goal. So the target. The target is to distribute the reception schedule. So let me get back one slide. The goal here is the following. Out of this M slot in the data part, okay, I want in a distributed way to assign these M slots to sensor nodes. For example, sensor number 1 gets slot number 2, sensor number 4 gets slot M, and so on and so forth. I want some way for such that all the nodes in the network can get to have one slot at least in the data subframe, which is dedicated for reception to that specific slot, sensor node. Okay? So the target is to split these M slots into all the sensor nodes which are out there in the network, okay, such that everyone has its own reception schedule. That's the target, okay? And the constraint I have is that I want to implement this splitting in a distributed way, which means that I don't have anyone telling all the nodes which slot to use, okay? So what I do is basically to use these slots in the signaling subframe, okay, and to define signaling messages which are conveyed in each one of the slots in the signaling subframe, okay, which are called BSP, which stands for broadcast signaling packets. So what I'm saying is the following. To get one node have one of these slots assigned, okay, all the nodes in the network must send some kind of signaling information in the signaling subframe slots, okay? And the type of information which is sent in each one of these slots, so the content of each one of these slots, is one BSP packet, okay? And the BSP packets have this kind of format, okay? So, is it clear so far? That is the target we want to achieve? Okay. So, each one of these BSP packets, which is again all these figure here, you have to imagine it as contained in one slot of the signaling subframe. Okay. And what is BSP is actually telling, okay, is basically what is the status of all the slots in the entire frame. Because if you look at the format of this BSP, you have an ID, which is the ID of the node which is sending out the message, say node number 4, okay? And then you have a kind of bitmap representation of all the slots in the frame. So the first, let's say, n fields of this packet, okay, they tell you what is the status of the corresponding slot in the signaling subframe as perceived by the sender of the BSP, okay? And the same stuff happens for the last m slots. So the last m fields of the BSP, okay, they're telling what is the status of the data slots as perceived by who is sending the BSP packet. Okay? So basically it's a bitmap, 0, 1 bitmap, you can see it, where 0 means that that slot, the corresponding slot is busy, and 1 that the corresponding slot is free for transmission. Okay? Clear? So just names, the fields which correspond to the signaling subslots or signaling slots are called frame information. Okay? The fields which correspond to the data subframe, they are called reception schedule information. So one is giving the status of the signaling subframe, and one is giving the status of the data subframe. Okay? Clear? Okay, so let's see how to use it. Okay? So this is basically what is sent out by all the nodes to build up this reception schedule assignment. Okay? And let's see with an example how this can be used. Suppose that you have a network which is composed at some point of time by sensor 2, 3, and 4. Okay, so sensor 1 is not in the picture yet. Okay? And suppose that sensor 2, 3, and 4, they already have achieved some kind of assignment in the signaling subframe and in the data subframe, which means that they already have some slots which is dedicated to their transmission, okay, in the signaling subframe and in the data subframe. Okay? Suppose now that S1 gets in, okay, and what you see here, the circles just represent the, let's say, transmission range, which means that S1 can hear everybody in the network, 2, 3, and 4, okay. On the other way around, S2 and S3, they cannot hear the transmission of S4 and vice versa. Okay, so it's basically the clustering of the nodes as far as the transmission range and reception range is concerned. Okay? So once S1 gets in, okay, to be part of the network, it really needs to have a reception schedule assigned. So it really needs to know when, in which slots, it can actually transmit and receive in the signaling and the data subframe. Okay? So to decide which slot is actually available, okay, it has to receive the status information from the other nodes. Okay? So what's the status information of sensor 3? So what's the BSP packet, the content of the BSP packet sent out by node 3? Okay? So node 3 is in range of node 2, okay? Which means that I expect to see in the BSP sent out by node 3, okay, that the slot in which node 2 is transmitting in the signaling subframe, okay, would be marked as busy, okay, because they can hear each other, okay? Which is exactly what is represented by this line here, which is the frame information, so the content, sorry, the bitmap representation, the first part of the BSP, so the bitmap representation of which slots in the signaling subframe are taken and which are free. Okay? So with this information, okay, node 3 is telling that slot number 1 in the frame, signaling subframe, is taken by itself, basically. Okay? Then it sees a couple of slots which are free, so no one is transmitting there. Okay? Then it sees in slot 4 the transmission of node 2, okay? And then the last two slots in the signaling subframe, they are again free. Assumption here is that the slots in the signaling subframe is, 6, okay? And I'm not showing here the second part of VSP, so I'm not showing the reception schedule information. So the bitmap corresponding to the data part, okay? So I'm only showing the bitmap corresponding to the signaling part. Clear? And then node 2 does the same. So node 2 at this point of time can only hear the transmission in the signaling subframe of node 3. Okay? Which means that the frame information sent out by, the BSP, the frame information contained in the BSP sent out by node 2 will be the same as the one of node 3, basically, because they can hear each other. Okay? What about node 4? Sensor 4 here is alone, which means that it only signals as busy the slot in the signaling subframe which is using. Okay? By assumption, this is the last slot in the signaling subframe. Okay? So when S1 gets in, okay, it receives the information, this kind of information, this kind of frame information from all the nodes which are in the network. Okay? And then basically it does the merging of this information to get to know which are the free slots in the signaling subframe. For example, merging means that it scans slot per slot all the frame information which it has received, okay, and it marks as busy each slot where at least one of the frame information it is receiving signal that slot as busy. For example, slot number 1 is busy because I have two guys which are telling me that there's actually someone using that slot. So this slot is busy. Okay. Slot number 2 is free because no one is telling me, or better, all the nodes are telling me that that slot is free. Okay. Same stuff for node 3. Sorry, for slot 3. Slot 4 is busy because I have two guys which are telling me that that slot is busy. Okay, so it can be used for accessing the signaling subframe. And then the 5th slot is again free, and the 6th slot is busy. Okay, which means that sensor 1, which is accessing the network, I would say, can choose at the next frame, okay, among one of the free slots to send its own BSP in the signaling subframe. Okay, and the free slots in this case are slot number 2, 3, and 5. Okay, in other words, if the newcomer sends its own BSP in one of these free slots, okay, it is sure that it cannot collide with any other node which is already there. in the signaling subframe. For example, in this case, the newcomer chooses slot 2 for accessing the channel, okay? Which means that it will just send out its own BSP in slot 2, okay? Clear? Question? So all these signaling subframe, yes?
What if there is an S5 mode in the transmission area of S4 so that S5 can reach S1 but cannot reach S3 and S2? And the FI of S5 has S4 at the last slot and something else at the first slot different from S3, so that S1 receives the FI from S3 and S2, telling him that S3 is busy for S3, and from S5 he receives an FI telling him that the first slot is busy for another one. When he has to transmit, when does he transmit for S3 or the other one? Is some kind of collision.
Okay, so let me clarify it a bit. So this is basically what happens in the signaling subframe. So in the signaling subframe, there's no data transmission, okay? Which means that what the sensor node here are doing basically is competing to get access to one signaling slot only, okay? Which means that S1 here means that this slot is used by S1 for transmitting data, not receiving data, okay? So if there were an S5 here, and this S5 here would have, for example, would signal that the first slot is occupied by someone else, okay? This has no effect in the newcomer, because the only information which the newcomer is interested in is whether the slot is busy or free, okay? Clear? So this is only the signaling part. We're not talking about data part. We'll see data part in next slides. So is it clear? So after this procedure, okay, which takes some time, we'll just evaluate the time in a few minutes, okay, all the nodes have one slot in the signaling subframe. So we did not talk yet about the data subframe, which is the most interesting one, okay? This slot in the signaling subframe, though, has some kind of nice property, okay, which is the following. A slot in the signaling subframe, which is assigned in this way, okay, is a reliable broadcast channel, which means that if I get a slot in the signaling subframe using this procedure, okay, I'm sure that if I transmit in that slot, all the nodes which are in my range, they will receive my transmission without collision. So it's a reliable broadcast channel, one-hop broadcast channel, okay? And this is nice because it's exactly what we need to actually distribute the slot assignment. So we really want to have a signaling phase where whenever we transmit, okay, we are sure that everybody is actually receiving it, or better, everybody which should receive it is actually receiving it. Okay? Clear? Yes?
Is the amount of n a fixed value? For example, if there are more nodes than n, what will happen?
Okay, that's a good question. So she's asking what's the dimensioning criterion for the number of slots, n, m, or whatever. Okay. Answer is we'll see in a few slides. Okay. To anticipate something, obviously n and m, okay, must be decided or dimensioned depending on what's the network size, okay, and the network topology. We'll see some guidelines in the next slides. Okay.
One question.
Yes.
Then the dimension is assigned statically.
Okay, that's another very good question. Let's say that the question is whether n and m parameters n and m are statically assigned. Okay, The answer is no, in the sense that you can change it at runtime, okay, but the let's say dynamics for changing NNM must be kind of slow. So you cannot change them too often, okay? Because whenever you have to change NNM, you have basically to rebuild the network all the times, okay? So you'd better dimension NNM well at the beginning, okay, and then only in kind of let's say sporadic events reshape NNM, okay, because it costs some time, okay. But in principle, you can actually choose NNM at runtime. Sorry, choose NNM dynamically, okay. Other questions? Okay, so in this way, again, we actually are able to assign a slot to all the nodes. Okay, sorry, a slot in the signaling subframe to all the nodes. Okay, if the slot is assigned this way, we are sure that this is a reliable one-hop broadcast channel. Okay, which means that in that corresponding slot, all the nodes can actually send out their own BSP. Okay, so that slot can be used, for example, to get information about the reception schedule, or pre-book, reserve some of the slots for the reception schedule part. Okay. So what's the use of this wake-up slot here, which we somehow kept hidden till now? So the idea is the following: if the network has a kind of regime operation, which means that all the nodes in the network, they all have one slot in the signaling subframe, and they all have their own reception schedule in the data subframe. Okay, so if the network is kind of static, okay, all the nodes will only switch on in the wake-up slot and in their own reception schedule slots, which means that the signaling subframe part is not used any longer, because it's somehow at the regime part. Okay? What's the problem? The problem is that we really need to have ways such that new nodes coming in can get part to the network, can become part of the network. Okay? Which means that we really want to activate the signaling procedure which I have just described to you, okay, only when needed, which means only when a new node comes in, and this new node must be aware on what's the status of the channel, such that it can choose its own slot in the signaling subframe and its own slot in the reception schedule. Okay? So the idea is, I want to activate a signaling procedure only when a new node comes in, or when we have to make changes to the network configuration, let's say. Okay? How to do that? By using this wake-up slot. Okay? Again, a wake-up slot is one slot in which all the nodes are active by contract. All the nodes are always active by contract. Okay? And as the name suggests, the wake-up slot is used by newcomer nodes, okay, to trigger the activation of the signaling procedure. Okay? Example. Let's say consider this very, very naive example here. We have two nodes, okay, and a new one coming in at some point of time. At regime, these two nodes are already part of the network because they entered sometime back in the past, okay, which means that they already have a slot in the signaling subframe, they already have a slot in the reception schedule, and since the network is actually running at regime, they only switch on and off at the wake-up slot and when they have to receive something, which means in the reception schedule. Okay, so they're not using the signaling subframe any longer. Okay. Still, the new node coming in must get to know what is the status of the network. So it really wants to trigger a signaling procedure to get a slot in the signaling subframe and a slot in the reception schedule. Okay. To do that, what node 3 does is first send power on this wake-up slot. So just to inject a beacon kind of message, which it's not actually a message, it's just a power signal. okay, in this wake up slot, okay. In the wake up slot, node 1 and 2 are active by contract, so they must be active, okay, which means that if a node receives power in the wake up slot, it is activated in the sense that in the next frame it will start back the signaling procedure, which means it will start back signaling what is the status of the channel as perceived by himself. In practice, node 3 enters the network, it sends a power tone in the wake-up slot. Node 1 and 2 overhear this tone, they are activated. So in the next frame, which starts here, okay, they will start sending their own BSPs in the signaling subframe. Okay? So node 1 will send out its BSP here. Node 2 will send out its BSP here. Okay? And the BSP is exactly what we have seen in the previous example. For example, it has this content here, this bitmap content of the frame information. Okay? Which means that after one frame, so better, after one signaling subframe here, the new node coming in can build up the current status of the channel. Which means that it can get to know on which slots are free and which slots are busy in the signaling subframe. And similarly, which slots are free or busy in the reception schedule. Okay? Because everything is contained into the BSP packets which are sent out in the signaling subframe here. Okay? So at this point of time, okay, node 3 can take a decision on which slot to choose for entering the network. Okay? So the next time, the next frame, which starts here, okay, node 3 can actually send its own BSP signaling packet in slot number 3 here, not 4 here, okay, in this slot here. Okay. Which means that it has gained access to the channel better. It has gained access to one slot in the signaling subframe. Okay. One tiny comment. So during the second frame, so the frame where node 1 and 2 send first their own PSPs, okay, node 3, okay, is keeping them active, which means that it will keep sending the tone in the wake-up slot. Okay. Why? Because it needs to know, basically, in the following frames, whether the access has been successful or not. In other words, tone here, the sending of these two messages is triggered. Okay. Tone here, node 3 is asking for the two nodes to be active again in the next frame. Okay. So it takes a decision here on which slot to access, which is slot number 4. Okay. It keeps sending a tone because it wants to know if the choice of slot 4 was fine or not, was successful or not. Okay. And how it determines whether the access was successful, just by looking at the frame information in the following frame, the last frame. Okay. And the rule is the following: if all the frame information which I see, okay, also see me, so also see my transmission, okay, it means that transmission was successful. Okay, so it's a kind of acknowledgement of the slot I've chosen, okay, in the previous frames. So once I get this acknowledgement, so once I get to know that both guys which I over here, they also overhear me, they also see my transmission, okay, I can set all the guys to sleep, which means that at this stage here, okay, I do not send any longer any tone in the wake-up slot, which means that everybody goes to sleep in the signaling subframe part. Okay? Clear?
How does node 3 knows when the wake of the slot is?
That's about synchronization, which means that, as I was saying, we assume to have this kind of synchronization somehow.
But
Okay.
node 3 is a new node.
Say again?
And node 3 is a new node, isn't it?
Say again?
Node 3 is new in this.
Yeah.
So,
So, as I was saying, we assume that you have a first protocol which is not part of SPERMAC, which is providing this clocking, okay? And then once you have this clocking, okay, you can just get to know when the wake-up slot is, and started training from there. Okay, this first protocol you can use whatever you want. So there are a bunch of protocols which are commonly used to get kind of clocking synchronization or slotting synchronization and stuff. Okay. Questions? So a couple of comments. I'm not showing here anything in the DSU. So I'm not showing here any assignment in the DSU, which there must be. Okay, so this is not shown, not because it's not used, but because it's just to give you the idea on what's the time frame for new node accessing the network. Okay. And the second comment is, as you can see, it takes some time. So it takes some time for node 3 to actually enter the network. Okay. And this time means also energy, okay? Because whenever you have a new node coming in, you have to trigger a signaling procedure, okay? And you have an overhead in terms of packets transmit by other nodes, which is energy consumed by other nodes to let a new node come in, okay? So it's always an energy efficiency trade-off, okay? Clear? Questions? Okay, so what about the reception schedule? So how do you choose the slots for receiving data? Okay, there's no, let's say, predefined optimal way to do that. Okay, the most common procedure is to implement some kind of one hop aware policy. Okay, so basically the idea is to choose a reception schedule which is non-overlapping with the reception schedule of your one-hop neighbors. Okay, which means that basically you don't want a node to be receiving in the same slot another node it can hear is receiving also. Okay, but again, you can be more conservative in this kind of approach, like defining a rule such that you don't want to use the slot for receiving, which are used by two hop neighbors, so neighbors which are two hops away from you, okay, or less, let's say, okay. But this is not part of the protocol. What is part of the protocol is the tools to allow a node to choose what reception schedule to implement. Okay. Clear? Okay. So we have the network running, which means that we have nodes which switch on only when they have to receive something, or they switch on at reception schedule slots of nodes they have to send something to. Okay. Suppose that two nodes, they have to send at the same time or in the same data subframe a packet to one single node. Okay. They know the reception schedule of this one single node, which means that they switch on at that slot, and they will send packets, they will send traffic. Which means that even if this is slotted, okay, you can have collisions in the reception slot of specific nodes. Okay, which means that you must have some way to randomize collisions, so to resolve collision. Okay, and what is implemented here is the usual back-off protocol, such that you defer, so you delay your transmission upon collision, okay, according to a random rule. So you choose the next the next frame to send traffic to one specific node, okay, uniformly in a window whose size increases as you go by colliding. Okay, clear? That's the same principle of the 15.4 backoff. Okay, the difference here is that it is applied on a frame time scale, not more on a slot time scale. Okay, so you try in one frame to access one reception slot. If you have success, fine. If you fail, you try at the following frame whose ID depends on this rule here. So it depends on this exponential kind of backoff rule here. Okay? Clear? Questions? Okay, so let's get very quickly to dimensioning, which is a question we had before. Okay. So we have to ask ourselves, as always, which are the parameters which somehow influence the performance of the medium access control. Okay. Actually, we should have done this exercise also for the other protocols. So, which are the dimensioning parameters? Let's do it now. So, which are the dimensioning parameters of 15.4? So, what is the parameter which influenced the performance of 15.4? Beacon enabled mode. It's on the framing sides, right? So how long is the cap, how long is the GTS, how many slots you have in the GTS, okay? How many slots you have in the sleep part, the duty cycle, what's the duty cycle, if you're talking about energy performance, and so on and so forth, okay? What kind of parameters you have in SMAC? In that case, you just have one single parameter, which is the duty cycle. So for how long you're sleeping and for how long you are actually active for receiving, right? What about here? So here, basically, the performances depend on, again, as in 15.4, on the framing. Okay. So generally on the frame length, how you structure your frame, what is N, what is M, and so on and so forth. As usual, performance depends on traffic, or better, your framing, your parameters must be dimensioned on the type of traffic you have. So you have application requirements, let's say, okay, and the performance depends also on the CRA, which is the collision resolution algorithm. So what's the effectiveness of the collision resolution algorithm to solve collisions, okay? And once you have to dimension this kind of three parameter, or better, two parameters and one application requirement, or a bunch of application requirements, okay, you have to account for the usual stuff, right? Energy consumption, delay, throughput, and so on and so forth. Okay? So let's have some kind of qualitative discussion on how to dimension the SPERMAC. Okay? So first of all, what is the achievable rate? So suppose that your performance, or your performance measure is the achievable rate. So meaning what is the equivalent data rate bits per second which you can deliver if you play the rules of SPERMAC. What is it? Forget that you have the formula there. Just ideally, what would you expect the data rate to be? Data rate is usually how much information you can deliver in the unit of time, let's say. How much information in what time frame, okay? So if we are talking about the data rate for receiving, so what is the equivalent data rate for a node who is willing to receive information, okay? This can be defined as the ratio between the reception schedule sites, so the amount of information which is conveyed or which can be transferred in one reception schedule, so a bunch of slots for receiving, okay, divided by the frame size. So how often the node has this reception schedule opportunity, okay? Which is exactly what is saying this Formula 1 here. So the maximum data rate, equivalent data rate for reception is basically BRS, which is the payload of the reception schedule, okay, divided by the frame size. Sorry, the frame duration, not size, okay? So the frame duration and the denominator here is basically how long the signaling subframe lasts, so n slots times the slot duration, TSS, okay, plus how long, what's the duration of the data subframe, so m slots times TDS, plus the wake up slot, which is the slot where everybody's active. Okay? As you can see here, slots may have different sizes. Okay? Even if in practical deployment, all the slots tend to have the same size. Okay? But in principle, you can design slots which are of different sizes in the signal subframe and data subframe. For example, it makes sense to have slots which are shorter in the signal subframe and longer in the data subframe. Okay? Clear? So, if our performance measure is the equivalent data rate, okay, what would you do to have higher data rate? You can make slot longer or better. You can send more information in the reception schedule, so you can increase the size of the reception schedule, okay? Meaning you move from assigning one slot for reception to assigning n slots for reception. So you multiply by 10 the equivalent data rate, okay? Or if you want to keep the reception schedule fixed, okay, you lower the frame duration, which means that you lower down n and m. So you make n smaller and m smaller. So basically, this is equivalent of playing with the duty cycle in 15.4 or playing with the duty cycle in SMAC. Okay, the shorter the time frame, the higher the duty cycle. So the longer time you're active, let's say. Okay, clear? The point is that you have some constraints on n and m, because as I was saying before, n and m are number of slots in the signal subframe and number of slots in the data subframe. Okay, so I expect, as your colleague was anticipating, that n and m must be somehow set depending on the topology of the network. Okay, which means that at least I expect to have if I have n nodes in my network, I expect the signal subframe to be at least n nodes long. Okay, otherwise some nodes cannot participate to the network. Okay, clear? So let's see how n and m can be actually set. Okay, or better, which are the constraints in setting these parameters. So let's start from n. N is the number of slots in the signal subframe. Okay. There is an n min, so there is a, let's say, lower bound on m, which means that n must be greater or equal than this n min, and this n min depends on the specific topology. Okay. The rule to decide to identify what n min is given a specific topology is the following. So n min is the size of the bigger 2-hop cluster in my network. What's a 2-hop cluster? Is a structure of nodes which is similar to what you see here. Okay, so a 2-hop cluster is a bunch of nodes in the network which have at least one node in common. Okay. For example, these two sets of nodes, it's sets of nodes which can hear each other, all of them. Okay. And these two sets of nodes, they have some overlap, which means that you have a couple of nodes here which belongs to both sets. Okay. The whole stuff here is a 2-hop cluster. Okay. It's a cluster of nodes whose maximum distance is 2-hop. Okay. Here. So why the n min here must be greater or equal than 7, which is the size of this 2-hop cluster? Why is that? Remember that n is the number of slots in the signal subframe. And remember that the slots in the signal subframe, they must represent reliable 1-hop channels, which means that all the nodes which have a slot in the signal subframe are sure that everybody in its neighborhood, one of neighborhood, receives its own transmission with zero collision probability. So why n min is 7 here? Let's do it reverse engineering. If we set n equal to 6, in this case here, okay, is it true that all the nodes have a reliable one-hop broadcast channel? No. Why not? Because if n is 6, if big N is 6 here, it means that at least 2 nodes in this structure, they will have the same slot. They will use the same slot in the signal subframe, right? Clear? So if any 2 nodes, if you choose arbitrarily any couple of 2 nodes and assign to these 2 nodes the same slot, there will be a collision at one of these 2 middle nodes at least. Okay? So in other words, the n min you see here is basically the minimum number of slots which you need such that you don't have any collisions in the broadcast transmission of the signal subframe. Okay? Clear? What about n? So once we have fixed n, which is actually telling us what is the size of the network. So what is the size, not the size exactly, but size and the geography of the network, the topology of the network. Okay. Once we have fixed n, not fixed, but let's say dimension n, okay, we need to decide what is the size of m, so the number of slots in the data subframe. Okay. And here we actually have a couple of numbers to be decided, okay, which is n min and n max. So if big N is fixed, okay, I really want to have m as low as possible, okay, on one side, because if m is low, let's say, the duty cycle is high, which means that the equivalent data rate is high. Remember the formula here. Okay, I have m at the denominator, which means that if this one is low, the equivalent data rate is high. Okay. On the other way around, I cannot set m too low, okay, because I have a topological problem. So I may have collisions, which means that I may have nodes sharing the same reception schedule. Okay. So I really have 2 extremes, or better, I can decide to set m, having in mind these 2 extremes, m min and m max. Okay, the m min, the m max extreme, so the upper extreme of this interval, depends on the specific application requirement. Okay, which means that if I increase m too much for a given reception schedule size, I'm reducing the equivalent data rate, which I'm assigning to the sensor. Okay, so if I have an application which is calling for 1 kilobit per second, okay, and I'm dimensioning an m parameter which is able to provide bandwidth for 500 bits per second, I'm not matching the application requirements. Okay, which means that I have to decrease a bit the m I'm using. Okay. However, as I was saying, m must be higher than m min, okay, which depends only on the topology I'm using. Okay, and the rule to set the m min, which is again topology specific, okay, is to set the m min as the size of the bigger one-hop cluster. Okay, where a one-hop cluster is basically a cluster of nodes which they all can hear one another. Okay, so if we take this figure here, So if you take this topology here, what's the M mean for this topology? What's the big M mean for this topology? Rule is take the bigger monocluster, so bigger cluster of nodes. All of them are interconnected, such that all of them are interconnected. Okay. Take the size of this bigger monocluster, and that's your M mean. So what's the M mean here? 4. Why 6? M mean, big M mean. Okay. So which are the monoclusters? You have one monocluster, which has 4 nodes on the right hand side, and you have one other sorry, it's 5, not 4. Okay, so you have another monocluster at the left hand side with 5 nodes. So M mean in this case is 5. Okay. So why you set the M mean to 5? So what's the rationale behind it? So what's the rationale? So why cannot we set M mean to 3 in this case? So what happens if we set the size of the data subframe to 3 slots in this case here? So what happens is that one of these, these 5 slots, they will have to choose among 3 slots, sorry, these 5 nodes, they will have to choose among 3 slots, which means there must be some node which share the same slot in the reception schedule. Okay, so what's the problem? Huh? Not really, it's not collision problem, because it's the slots which are chosen for receiving data, not transmitting data.
One will receive others' data. One node will receive others' data.
Exactly. So if 2 nodes are active in one slot only for receiving, and they're active only in that slot, it means that they can't communicate one another, right? So it's impossible if they have the same reception schedule for these 2 guys to communicate, ever. Because they will be active in that slot for receiving, okay? So this M mean is actually the minimum number of slots, which ensures that you don't have this situation. So it ensures that all the nodes in a one-node cluster, they can actually exchange information one another in the data subpart. Okay? For example, if we take the grid network, like the one you see bottom right in the slide, okay? In this case, the maximum one-node cluster is of size 2, okay? Which means that the M mean is 2. You need, in that case, at least 2 slots in the data subpart, such that all the nodes which are in range can actually exchange data one another. Okay? Clear? Questions? Doubts? Questions? Okay, so that's just a figure which shows how the data rate, the equivalent data rate decreases with M and N. That's just dimensioning, plotting some data. Okay. So you have questions on this part? Okay, so in the last, 5 slides, more or less, there is an energy model for SpareMac, which we just skip here. Okay, skip means that it will be not part of the exam. Okay, if you want to have a look at it, you are more than welcome to do that. But we will not go through the calculations of the energy consumed by SpareMac. Okay. So this concludes somehow the part on medium access controls or non-standard medium access control. Let me repeat again that it's not, it it is not basically comprehensive on the medium access control protocols available for sensor networks. So you may find hundreds of more medium access control protocols in your career, life, or whatever. Okay, so don't think it's just what you have told to you. But still, these three protocols which we have chosen to analyze, they somehow convey all the main features of most of medium access control protocols for sensor networks. So they're kind of representative ones. Okay. So what we do now is just to leave aside the medium access control protocols and move to introducing the 6LoWPAN stack. Okay. So let me just switch slide set. So, what is 6LoWPAN? As I was saying in one of the very first classes of this course, 6LoWPAN is basically the let's say, competitor or the alternative communication protocol stack rather than ZigBee. Okay. Which means that it is basically promoted and standardized by the IETF, which is the Internet Engineering Task Force, so the guys who are actually standardizing the internet. Okay. And the main goal, just to cut it short, is basically to reuse all the protocols which are used in the internet also on sensor nodes. Okay. So to move or use the IP, the networking layer of the internet, also to interconnect sensor nodes and sensor nodes with the internet. Okay. So the reference architecture which you should keep in mind is the one you see here at the bottom right of the slide, okay, where basically at the lower layers you have 15.4, which we know, okay, and then at the upper layer, starting from the networking layer, you have, let's say, acronyms, so names of protocols which you should have seen in classical networking courses. So you have IP, you have UDP, you have ICMP, and so on and so forth. Okay. Few comments here. Physical and MAC layer are common to with respect to ZigBee. Okay. These two layers, though, can be actually changed with something else. So 6LoWPAN is really what is above the medium access control layer, and you can use 6LoWPAN also coupled with other medium access control and physical layer protocols other than 15.4. Okay. But this is the reference stack which is proposed within the 6LoWPAN standards, okay, which are internet standards. Second comment. At the networking layer, okay, you have IPv6. So you see there IPv6. Okay. However, as we will see, and this will be the, let's say, goal of the next this lecture and next one, this is not plain IPv6. This is not the IPv6 which runs in the internet, but it's something kind of more compressed version of IPv6. Okay. Which means that what 6LoWPAN does, or most of the work of 6LoWPAN standardization, is to make classical standards like IPv6 compliant to the resource-constrained environment, which is typical of sensor networks. Okay. Second comment: if you look at above the networking layer, okay, for example, you look at the transport layer, okay, you see there that you don't have TCP any longer. Okay. So the reference stack of 6LoWPAN is mostly based on UDP. Okay. I assume that you know the difference between TCP and UDP. Okay. So who does not know difference between TCP and UDP? No one. Okay. So everybody knows what's the difference. Okay. We'll get back on how TCP has been dropped later on, but the idea is that it was too heavy. So it was a protocol too heavy in terms of signaling, in terms of overhead, in terms of procedure to be supported by 6LoWPAN networks or sensor networks. Okay. So that's the reference stack. The plan for this course is to see into the details the networking layer and transport layer. Okay. Have a look also at the application layer. Okay. Meaning that besides defining the network transport layers, 6LoWPAN also provides some APIs, some, let's say, guidelines on how to design application layer protocols. That's different than what Zigbee does, which actually provided the full-fledged application layer protocol in terms of profiles. Okay. What 6LoWPAN does is just to give you application layer protocols which are similar to those of the internet, like the HTTP, okay, properly adapted again to the sensor network world. Okay, so we spent some time talking about the COAP, which is the constrained application layer protocol dedicated to the 6LoWPAN stack. Okay, and then the last thing we will see in 6LoWPAN is basically the routing issue. Okay, which is somehow hidden in the stack where you have a routing protocol. We'll see that coupled to this protocol stack, the 6LoWPAN standardization bodies are also defining a specific routing protocol which is called Ripple RPL, okay, which is specific for 6LoWPAN networks. Okay, so that's the complete plan for the next couple of weeks or lectures in this course. Okay. Okay, let me just keep some marketing slides. Okay, to get to the business here. So as we did for Zigbee or for 15.4, the first thing we have to keep in mind or define is basically the types of networks which are supported by 6LoWPAN. Okay, so what kind of networks are actually available for being defined and managed by 6LoWPAN kind of protocols. So, in the slide you see some of these supported networks. Okay, you have basically the most common network, which is called an edge network or a simple network or a stub network, different names, where you have basically a bunch of sensor nodes. So these guys here are our sensor nodes. Okay, and these sensor nodes, okay, are divided into pure edge nodes and what I call routers in the internet jargon, so relaying nodes, let's say. And all these guys here are connected to what is called an edge router. Okay. As you can see, also the names start changing with respect to Zigbee. Okay, and they start using names which are more internet compliant. So we're talking about routers. We're not talking about any longer on Zigbee coordinators or this kind of stuff. Okay. So the simple LoWPAN configuration is like this. You have some nodes, you have an edge router, okay, and this edge router is connected through some kind of internet technology to a backhaul router or a backend router in the core internet. Okay. The second type of network is what is called an ad hoc LoWPAN, where basically the router is dropped. So it's a, let's say, self-standing network without any connectivity up to the internet. Okay, so nodes are just self-standing there, doing some kind of jobs. Okay, and the last type of network is what is called an extended LoWPAN network, which is basically a simple LoWPAN network where you have two bubbles, two networks. Okay, which are somehow interconnected through a couple of edge routers, okay? And the two edge routers are actually coupled among themselves through some kind of backbone link, okay? This is kind of equivalent, if you think, to, for example, Wi-Fi deployments, where you have different access points which provide services to different networks underneath, okay? And the different access points are interconnected through some kind of backend technology, okay, to form an extended distributed service set, what is called. Okay, so a larger Wi-Fi deployment. The difference, I mean, the specific feature of this kind of network here is that you might have multi-hop paths within each bubble, which means that this guy here, to reach the edge router, might be forced to have multiple hops, which is totally different than what happens in Wi-Fi networks where you just have one hop to the access point, and that's it. Okay? Clear? And the same stuff happens for simple open networks. So also in simple open networks, you might have multi-hop connectivity from nodes to the edge router or the gateway to the internet. Okay? Questions? Okay. So, let me close for today on this concept of adaptation features. Okay, and we will get back on this concept more practically next time. So, just to point out where we stand. So, we said that we are actually here. Okay, and we want to fit UDP over IPv6, okay, into 15.4 frames, packets, or protocol stack, and so on and so forth. Okay. So the first thing is that a problem of sizes, dimension of packets of frames. Okay. If you remember, 15.4 frames, okay, were 100 bytes long in the best case. I mean, the payload part of 15.4 frames were around 107 bytes. Okay. So the first problem 6LoWPAN has to solve is actually to fit longer IPv6 packets, which can go up to 1200 bytes, okay, into 100 bytes frames of 15.4. Okay. Which is the main and core problem solved by 6LoWPAN at the networking layer. Okay. So how this problem is solved? In two ways. Let me go forward. The first functionality which is introduced by 6LoWPAN is called header compression. Okay, so the problem of these, let's say, too long packets to be fit into short containers is solved in two ways. The first one is to reduce as much as possible the headers of the internet protocols like UDP and IPv6, okay, such that most of the signaling information is somehow dropped or properly formatted or compressed, okay. And I mean, this takes care of reducing the signaling part of the packets, so the header part of the packets, okay. Still, even if header compression is implemented, it might be, or it is actually, in practice, in reality, that still the information, the packets which are sent down from the IPv6 down to the 15.4 containers, okay, they're still too long, okay, which means that they need to be fragmented somehow. And the other adaptation functionality which is implemented by 6LoWPAN is the fragmentation, okay, which means that IPv6 MTU, maximum transfer units, or packets, okay, have to be fragmented such that each one of the chunks of these packets fits exactly one 15.4 frame. Okay. So next time we will spend some time on these two adaptation functionalities, starting from the compression, okay, just to see how 6LoWPAN adapts to 15.4, let's say, resource limitations. Okay. So I guess we can stop here for today. I'll see you next week. Okay? Thanks.